Well, good morning. This is 9:34 on Tuesday, the 13th of September, 2016. Should be having Math 238 class right now, differential equations, and I'm the only one in the room, so sorry about that, but we're going to continue. Did want to give you a couple of announcements. You might not hear them until after it's over with. But normally my office hours today are from the end of my linear algebra class, which is at 12:15, until 4:45. Technically, that's when my office hours are. However, today, I don't know if you've heard about this or not, but ITT Tech closed. That was here in Bessemer. Don't know exactly where, but I remember when they were building it, I was hearing people talk about it, what was going up there. Then it turned out being ITT Tech. And a lot of people thought it drained students away from us because we were Bessemer State Technical College back at the time, then later Lawson State Community College, but we still had technical programs. Well, ITT Tech closed at the beginning of this term, this fall. Just absolutely did not open their doors for fall students. So therefore, the students they had who were in the middle of programs or whatever, they weren't able to finish. So we are now trying to entice some of those students to come to us. I'm sure that's not how they want us to say that, but it seems like that's what we're doing. So we're having an open house today. For some reason on the Birmingham campus, that's our main campus, of course, but ITT Tech was out here. So we're having the open house on Birmingham campus today at 3 o'clock. I don't know how long it goes till, but I'm supposed to be there at 3. So normally my office hours are here from 12:15 until 4:45, but today I'll have to be leaving no later than 2:30 in order to get to the Birmingham campus by 3 o'clock. Now, I'll be there the rest of the afternoon. I can't tell you where I'll be. I know that the open house, I think, is in the, I believe in the ACAT building there on the Birmingham West campus. So I assume that's where I'll be at 3 o'clock. And but if there's not much for me to do, I don't know how much there'll be for me to do. I'll either be in the ACAT building or back in my office in room B122. So this afternoon from 2:30 on, I will not be on this campus. I'll be going home from there, however late I'm there. I've got to leave by 5:15, I believe. So I don't know how long the thing is going to last or how long I'll need to be there. Okay, so that's that. Then tomorrow, we're having the open house on this campus. That open house is going from 10 until 2, and I'm in class at 10 o'clock. I'm in class at 11, trying to remember I'm in class from 9:30 until 11:10. And then I have lunch from 11:15 to 12:15, and then I'm in class from 12:15 till 1:55. So basically, except for my lunch hour, which I'll be wherever I need to be then, we will be, I'll be unavailable probably for office hours in that lunch hour, and then I'll miss, the last 5 minutes. I doubt if they'll still be there when I get there. So anyway, hopefully, I can't imagine why they would need me there anyway, but they said we're supposed to be there. So anyway, just announcing changes of office hours because of these open houses. All right, Cameron did come in. I wasn't here all by my lonesome. What's that?
Sorry, I was running late.
Yeah, I had troubles getting here this morning too. Just wanted to announce, join the math team. The first meeting is, as far as I know, from 1 to 2 today. Has that changed? I mean, Friday. I'm sorry, Friday.
Yes.
Is that still 1 to 2 on Friday? Have they said where?
260 something?
On this campus?
Yeah.
Okay. All right. Okay. So it's going to be on this campus.
Yeah.
This announcement didn't specify that. I figured it would be here, but I wasn't certain. Okay. So that'll be on the Bessemer campus from 1 to 2. I've got a meeting that's supposed to end at 1 o'clock over in the Ethel Hall building, but those meetings typically never end on time. So I may not be here at the beginning of the meeting, but if the meeting was going to be on Birmingham campus, I'd probably miss it completely. So anyway, that would be down in 261 probably, I'm guessing. Or 263, I think, 263.
It's 260 something.
Okay, that would probably be 263, 1 to 2. And then Miss Lawson's state coronation will be Thursday, October 13th, exactly 1 month from now, at 7 o'clock, just next door here at the Bessemer Civic Center. And are you participating?
No.
Oh, no, okay. All right. Now, I think we're set up and ready to go. We are already recording.
Have your projector on?
You know, I usually don't when nobody's in the room, so I hadn't turned it on since you came in. I swapped the lights too.
Oh man, they smudged up that board really quick, didn't they?
They do what?
They smudged up the board really quick.
Yeah, that's a big problem with this. People have been griping like crazy. They put these new sheets on all the boards, and they're worse than the previous. Upstairs, they said, "Don't touch ours. Leave them alone." And we didn't know that to request that. So
Have you tried the spray?
I haven't yet.
That might.
Yeah, I'm hoping it will, but you see, I don't know what might loosen the glue into that. So I'm a little bit afraid to try, but I think we're going to have to because it's not good. All right. But you see, I usually just use this so I don't mess up the boards, but Dr. Bryant will.
Yeah, but it's coming through.
What's that?
Look at the projection. Look at the projection.
Yeah, I know, it's awful. Okay, so I've got to get that corrected. All right. Okay.
I think we're on example 3. Page 48.
Yeah, but actually I probably need to say a little bit before we get there. I was reading that before in the time I had between classes. I tell you, PowerPoint has been so incredibly slow today. And I've got to go through all this.
I can already see I'm going to be going to eat something here.
Okay. We're running late and skipped breakfast too, huh?
I had a banana.
The banana, okay. Banana is rapidly disappearing, huh? Where is my
I think it just made me
slide?
hungry.
There we go.
Made me realize my hunger.
Yes. It's called an appetizer. Okay.
Yeah.
All right. Just when we're beginning to do first order differential equations, separable equations, we've lost a solution, losing a solution. Some care should be exercised. You got to see that where that reads those 3 lines? Yeah. In separating variables, since variable divisors could be 0 at some point. Okay? They give this example. What if you had, okay. What if you had dy dx equal to some function that's g of x and h of y? Okay? Now, what our technique has been so far is get the y, and since these are multiplied, you can separate those by dividing your h of y and
Putting it
in differential form. Yeah, so that would be dy over h of y is equal to g of x dx. Okay? Now, the problem arises is, what if there was some value for which h of y was 0? Well, this is still a legitimate differential equation, but not the next one. But you did that, okay? You created the problem there by dividing by 0. So in that case, you have to stop and say, wait, for what values are h of y equals 0, that means at that point your slope is constant, 0, yeah. So your function is constant. So d of y is a constant function there at that value. So that becomes what we call a singular solution. Remember, we ran into that earlier and just going through all the nomenclature. That's what we got. You can't throw those away, okay? But then you proceed to do this. This is probably going to give you something. You know, it could have logs in it, could have other things. But of course, your y couldn't be 0 then, because those would not be allowed. And you integrate this and go on with that. And that could be 0, and that's fine, you know. But they would all show up in your solutions, okay? But the h of y may show up there where that is equal to 0, or it may not. You can't throw them away if they are. That's called losing a solution, okay? And and I think they thought they gave an example, but they didn't. Let's do example 3.
It says the title of it, losing a solution. So
What's that?
the title of this one is
Losing a solution, exactly, okay? Why did I go through this route? I'll set some there, I'll do it. Okay. dy dx is equal to y squared minus 4. Okay? Now, before you do anything else, you look at that and say, is there some place where y would have to be some constant value? And that would be a solution here. And that's pretty obvious as 2 possibilities.
2.
Say again?
Y equals 2.
Y is equal to 2
And
or negative 2. Those are singular, well, later we'll determine if they are, but they are solutions, okay? dy dx is 0, and that means y is a constant, and the slope is 0. Okay, Victor's here. All right. Now, we're on example 3, bottom of page 48. We proceed as we would normally do, and that would be dy over y squared minus 4 is equal to dx. Okay, right? Okay, and then we try to integrate each of these. Okay, what would we get? How would you integrate that? Partial fractions, you're absolutely right, okay? So you would have to go off to the side or somewhere here and say 1 over y squared minus 4 is equal to what? How would you do that?
1 over y squared.
Okay, a over,
Oh, yeah, a over.
not y squared.
Y, y plus 2 and y minus 2.
Plus b over y minus 2. Right. Okay? We split that fraction, factor it, and see if we can come up with a value for a and b. All right. Now, there's a couple ways you could do this. The way I think we determined was the easiest way. Yes, exactly, which is the product of y plus 2 times y minus 2. Multiply both sides with that, and over here you get a 1, right? Over here you get a y minus 2 plus b times y plus 2. Okay? And then what is the clever little device we use?
Something equals 0?
Yes.
A or B? No, it's the y.
The y! Well, not equal 0, but we let it equal something that we otherwise would. Yes, we let it equal plus 2 and we let it equal minus 2. Okay? And when it's equal to plus 2, what do we get? 1 is equal to y is equal to 2, that would be 4b. So b is equal to, second, 1/4. And if we let it equal minus 2, you get 1 is equal to negative 4a. Okay? So a is equal to negative 4. Yuck! Negative 1/4. This is such a strange thing. So this function then becomes, that becomes the integral negative 1/4, that was our a, dy over y plus 2 plus 1/4, integral of dy over y minus 2, that's equal to, what's the integral of x? Dx would be x, sorry, okay. All right, now, I haven't done my constants yet. I'm just going to hang off with those for a minute. And let's see what we've got here. This would be, what would be the antiderivative of y plus 2, 1 over y plus 2. Yep. Yeah, quit doing that. Okay. Okay. Plus 1/4 times the natural log of y minus 2, and that's equal to x. Okay. This is so bizarre. All right. Now, let's clear some space here, I guess. Let's clear this because we finished using that. Let's see if, what's that? Yeah, why don't we do that? Because we already got everything we needed there. Okay. Takes way too long. Okay. Now, let's play around with these expressions. This would be the log, natural log of, I'll keep the absolute values for now. We may not need them in a bit, but y plus 2 to the negative 1/4 plus log of y minus 2 to the positive 1/4. Remember, that's one of the things of logarithms, rules of logarithms, okay? And that's equal to x. Okay. Now, sum of two logs is the, yeah, well, yeah. Let me go back and change something ever so slightly here. Let's, yeah, the negative log. The difference of two logarithms is the quotient with the positive on top. So this is also the log of y minus 2 to the 1/4 power over y plus 2 to the 1/4 power is equal to x. Okay? Now, if we don't like having the logs in there, what we can do is take the e of both sides. And that will undo the logs, so then you have the ratio y minus 2 to the 1/4 over absolute value of y plus 2 to the 1/4 is equal to e to the x. Okay. Now, I think this is where, in fact, maybe right up here is where they introduced the c and said x plus c, and then that would have been e to the x times e to the c. E to the c would have been your new constant. So basically, here's your constant here. Put it there. C e to the x. Okay. I think that's how they usually do this. Now, if we want to solve that for y, we'll magically lose the absolute value bars because they sort of act like you really don't need them in the first place. What you could do, you could make that a plus or a minus c. This is a little shady here seeming, but it is legal. If you take out the, well, I thought I had the erase bar, but it didn't come up. There we go. If you take out this and put in parentheses in their place and make a plus or minus c, you get the same effect. Okay. In other words, where that had to be, where you had to take the negative of this to make that positive, and put that minus over here, right? Where it was positive. So those are your two constants, plus c and minus c. Okay. Now, what we're going to do is raise both sides. Another way to write this, of course, would then be y minus 2 over y plus 2 to the 1/4 power is equal to c e to the x plus or minus c e to the x. All right. And now we raise both sides to the 4th power. Okay? And we have y minus 2 over y plus 2 is equal to and if you raise it to the 4th power, well, we'll leave it for right now. Actually, what was c to the 4th is now going to be our new c. E to the, so I did it a little early, to the 4x. Okay. Now, that's going to give us two possibilities here. Well, let's multiply both sides by y plus 2. Just have the c e to the 4x here times y plus 2. Okay. That would be y minus 2 is equal to c e to the 4x y minus 2 c e to the 4x. Okay. Now gather your y's together. That would be y minus c e to the 4x y is equal to 2 minus 2 c e to the 4x. Okay. Yeah, this is a little messy. I don't have enough room to write. What you did is multiply both sides of the equation by that. Okay. Then multiply this across there. CE to the 4xy plus CE. Ooh, that is a plus sign, isn't it? Okay, sorry. So plus, so that's going to make this a plus. Okay, sorry. I think I got it right now. Okay. So what I did, CE to the 4x this, plus 2CE to the 4x. Okay? And then get my y's together, which is y minus CE to the 4xy, bringing that to this side, and then adding the 2 to this side. So my terms without y's are over here. Factor out my y here, and that gives me, can't I write somewhere else? Let's see. Let's go back and erase. Let me just erase up here too. Okay. I hope I'm not losing any generalities here. This thing, I don't know why, but everything is slow. And if I'm not patient, okay. So this would then be y times 1 minus CE to the 4x is equal to 2 times 1 plus CE to the 4x. Okay? All right. And then divide by this thing, 1 minus CE to the 4x. 1 minus CE to the 4x. Okay? These go out, and you have y is equal to 2 times 1 plus CE to the 4x over 1 minus CE to the 4x. Okay. And that's what they got. They didn't put parentheses in front, but I did. All right. Now, if you'll notice here, at a judicious choice of your constant c, as in c is equal to 0, then these two terms become 0, and then you have y is equal to 2. Fantastic. So you didn't lose that singular solution. It wasn't a singular solution. It's included in your family of curves here. But try to come up with some way to get the minus 2 there. You can't do it. Okay. So your solution is either y is equal to 2, or negative 2, or y is equal to this. And this is a family of solutions with the parameter c. Y is equal to 2 can be included in that. Y is equal to negative 2 cannot.
So we lost the solution.
You lost the solution. What did we do with it? I know we had it here somewhere. There it is. Now, the thing I find so amazing here is all they say. However, y is equal to negative 2 is a singular solution. It cannot be obtained from 6, which is what we were doing, for any value of c, any choice of the parameter c. This latter solution was lost early in the solution process. Inspection of the equation that we had there clearly indicates you must preclude y is equal to plus or minus 2 in those steps, but they never say how they want you to write that solution. It's either minus 2 or this. But they don't ever write that down for you and say, this is what you got to do.
So basically they were looking for the solution. It didn't exist.
Huh?
They were looking for the solution. solution that didn't really exist.
No, it does exist, but it was lost if you just did this procedure without taking into account that. You didn't lose the 2, positive 2, but you did lose the minus 2, so your solution is either y is equal to negative 2 or y is equal to this for any value c.
So that's the whole thing.
That's what you have to say for the answer until they tell us something else. But right now, that would be the only way I can see to do it. All right, let's move to example 4.
I like the answer negative 2.
What's that? Yes.
If I could have just stuck with that, I think I would have.
All right. All right. So let's do another one. Solve this. E to the 2y minus y times cosine x dy dx is equal to e to the y sine x. Sine 2x, sorry, I can't read. Sine 2x. And you have an initial condition here, y of 0 is equal to 0. Okay. Now, what you want to do is to get all your, that's a function of y, a function of x, your derivative. Function of y is function of x. Everything's multiplied, so therefore let's separate our variables. Keep the y's on the left, move the x's to the right, move y's to the right, left, So this would become, you would divide both sides by e to the y. Is that a problem? E to the y is never 0. No Sweatskis there. But over here, you would have to divide by cosine x. Oops!
That can be.
Yeah, that would be what?
Can be.
That can be 0. And where is it 0?
Pi halves.
Yeah, your half pi's. So y, but let's see what happens. Since that's over here on the left, to begin with, if that's 0, the problem makes no sense. It's 0 is equal to e to the y sine 2x, so it's just every place that sine 2x is 0, because e to the y is never 0. So then what you have is sine 2x is equal to 0. So the y's aren't even involved with it there, okay? So I think that we'll be okay doing that alone, because that's not going to introduce any problems for us, I don't think. That's divided by cosine x. Okay? Oh, I forgot to divide this side by e to the y. I started talking about it not giving us any problems. All right, these go out here, those go out here. We write it as a differential. So we have e to the 2y minus y over e to the y dy is equal to sine 2x over cosine x dx. All right, I don't know about you, but this looks fairly doable, okay? At least in the short run, okay? Looks better than that one does. What do you reckon we're going to have to do with that one? Second? On this right here.
Oh, that.
Yeah. Oh, no, okay. Yeah, I think this is sort of doable. We'll come back and fiddle with that. What are we going to have to do with that? Second?
That makes me, I want to change it from sine to cosine.
But you can't do that because it's different arguments. So there is something called a double angle formula for sine. You remember what that was? Okay, I hope you didn't sell your calculus books. This is 2 times sine x cosine x. Do you remember that? Okay, how about this? Sine of alpha plus beta. Remember what that was? Sine alpha cosine beta plus cosine alpha sine beta. You remember that? Vaguely. All right. Who did you have for trig anyway? No, don't answer that question. Okay. That was our double angle formula for sine. Okay? Oh,
I can't
here's
remember.
this.
This is one of the ones that
Okay.
you look it up.
Yeah, it may be. But that's what I'm saying. I hope you kept your calculus book, because I think I've glanced through here and so far have not found my any of those what I consider your trig identities. I just don't see them in here. Let me see if they're in the index anywhere here. Trigonometric identities. I don't see any. Yeah. That's all stuff we'll be using here, so hopefully you hung on to you. Okay, but let's go back here. If you remembered this, and you may not have, that's what your sine of alpha plus beta. What if alpha is equal to beta? Then this would be sine of 2 alpha, right? And then this would be sine alpha cosine alpha plus cosine alpha sine alpha. That's 2 sine alpha cosine alpha. So sine of 2x would be 2 sine x cosine.
Yeah.
Okay. All right. Now let's see if that cleans up things a little bit. Well, if we do this division, this will be e to the y. E to the 2y over e to the y would be e to the y. Okay? Minus y over e to the y dy equal to, and here your cosine x's go out, which is sort of a nice thing, because if they were ever equal to 0, they're not anymore, because they're not there anymore. I mean, you don't even have them anymore. So you're not going to worry about them. So this would be 2 sine x dx. And now that's quite nicely doable. It's the other side that's now more difficult, okay? But let's see what we can do with that. Well, we can split that into two integrals. The integral of e to the y dy minus the integral of y over e to the y dy equal 2 times the integral of sine x dx. Okay, the first one's not a problem. This one, though, is beginning to get on my nerves. Okay? Because that's a problematic integral. Okay? What can we do with that? One thing I would do is probably rewrite it as integral of y e to the minus y dy. Okay? Now, where might you go with that?
I don't think substitutions can work.
Substitution, I don't think will work either. I agree with you.
It's one of the ones that we use towards the end.
It's sort of beginning. Yeah. Techniques of integration. Well, maybe it's near the middle. Okay. Integration by parts is what I would try. Okay, because it's a product. Products usually, that would be one thing to try. Okay? Now, I think I'm going to erase some of this, because we don't need this anymore. Now that we know that, I don't remember why that y was up there, but it's gone now. Okay. All right. How does this work then? Integration by parts, you remember? Okay. basically, you split it into two pieces. One you're going to differentiate, one you're going to integrate. So you want this one to simplify when you differentiate. This will not get any worse when you integrate. Which may want you.
So we would need to differentiate y.
Okay, so you let u equal y and dv equal e to the minus y dy. Okay? Then, what will you do with the u? Du is equal to dy. Right? Right, 1 dy, which is dy. Over here, your v would then be negative e to the minus y. Okay? Now, you don't need plus c's or anything here. We'll take care of that later. Okay. Then what do you do? Back your original integral that you're trying to do, you write that first as the product of these two, u and v, and that would be a minus y e to the minus y minus the integral of du of v du, okay? Yeah, except the minus with some subtraction, the minus there would make that a plus e to the minus y dy. You're absolutely right. Okay? All right. So this one becomes e to the y minus that we just did would be a minus would be a plus y e to the minus y. And then when we integrate e to the minus y, you get a negative, but you had a minus sign there, so that's another plus e to the minus y, okay, is equal to 2 times, what's the antiderivative of sine x? Second? Negative cosine. Okay. All right. And then you'll probably have a plus c somewhere in here. Okay? So. Yeah. Well, that's what separation of variables will usually do for us. The thing is, can you, in any way whatsoever, isolate those variables? And that really looks like perhaps a fairly difficult thing to do. Okay? So let's not. Okay? Remember, this problem came with an initial value. So let's just plug in. Let's just call it a plus c here. It doesn't matter where you put it, but let's just call it there. And let's see what happens if we do our initial value. So when x is equal to 0, your y is equal to 0, right? So when that first term's equal to 0, y is equal to 0, e to the 0 is 1 plus 0 plus 1, okay? Didn't know we'd be doing such high-level math today. 1 plus 1 is 2, is equal to, what's cosine of 0? 1, so that would be a minus 2 plus c, right? All right. Let's add 2 to both sides. This is 2 plus 2. That would be c is equal to 4, right? All right. So our final solution is e to the y plus y e to the minus y plus e to the minus y is equal to minus 2 cosine x plus 4. There's your solution. Okay. It's a what do you call it? Implicit, you might say, solution. You can't separate and solve for y, or you kind of could solve for x if you wanted to, but who would want to do that anyway? So you just basically leave it about like it is here. They wrote the 4 minus 2 cosine 2x. I mean cosine x. Now, they show in your book, you don't have a book yet, do you? Yeah. A whole family of solutions for different values of c. Okay, they're called the level curves of this function that we had here for various values c. And when c is equal to 4, you have the one level curve that goes through the origin, 0, 0. And that is your solution. See, all those are solutions for various values of c, the pink lines. But when c is equal to 4, then this is the one and only one solution. That one right there. Why they drew c is equal to 2 on there, I'm not real sure. Okay. Okay. The other curve in the figure is the level curve g of x equal 2, which is a member of the family blah. It satisfies y is equal to, y of 1/2 is equal to 0. Pi half is equal to 0. So why they threw that in, what if your initial condition was different? I guess that's what they're saying, or boundary condition is different. Okay. And then they start off on this. If an initial condition leads to a particular solution by yielding a specific value of parameter c in a family of solutions for a first-order differential equation, there is a natural inclination for most students and instructors to relax and be content. However, a solution of an initial value problem may not be unique. We saw that in example 4 of section 1.2, which is so far back that I don't remember it. And they reiterate that here. Wow. The trouble is, in their problem here, what in the world is that A? They sort of spring an A on us. It's not the constant, that's C. Or is it? I don't know why they introduce a new constant here. Parameter A.
I think it's showing the translation of the curve.
Yeah.
Because if you look at figure 2.4, it shows
Right.
A equals 0 and then it's moving over from there.
Yeah.
It's like the translation.
Yeah, and that's what you would get from their solution that they list here. So where did they get that parameter A? Unless they changed, I guess what they did, looking at this, I guess they let A be 4C maybe. Maybe that's what they did. That's maybe what they did. But anyway, as soon as you get comfortable with something, you say, but this could happen and you have to watch out for it. So there's another something could happen you have to watch out for. All right. Now.
I'm kind of scared of these tests. Some of these examples is just like.
I know. I chose this book, well, for a couple of reasons. I went through several that were just way, way hairy books. They covered way more than what we needed. This one, First Course in Differential Equations, that sounded more down our alley. I also found an instructor at, I believe it was Shelton, and she was talking about teaching differential equations. What book? Because I've been to like three or four. And she said she liked ZIL. And I said, I just got ZIL in, but I hadn't had a chance to look at it. It looked like what I needed. And sure enough, the table of contents, if you look at what our course description calls for, basically Chapter 2, Chapter 4, Chapter 7, and Chapter 9. And that pretty much covers what our course description does. So there's nothing in our course description that says we do too much with modeling. So I left off those chapters. Not that they're not decent; they're good chapters. But and then we did nothing on. Didn't say we needed to do anything on series solutions, so I left off that one.
Basically, most of the idea is to put it differential form and then
Right.
it all back up into get it.
At least so far. All we're doing is separable equations so far. The next section, well, wait. Yeah, we got a little bit more to do in separable. This is solutions defined by integrals. Okay? And that's what the next little topic is. So let me clear the ink from the slide. If G is a function continuous on an open interval I containing a point A, okay, then for every x in that interval I, and this is basically fundamental theorem of calculus part 2, I believe, d by dx of the integral a to x gt dt is equal to g of x. Okay? In other words, when you take the derivative of an integral, you get what's inside evaluated at the variable x. Okay? X is a variable here. A is somewhere. This is defined in the interval. X is in the interval. A is in the interval. So if the function is continuous that interval, if you can integrate it, then differentiate it, you get back what you started with. G of that value x. Okay. That's fundamental theorem of algebra part 2, I believe it is. You might recall that the foregoing result is one of the two forms of the fundamental theorem of calculus. Okay. In other words, that part, integral from a to x of g of t dt is the antiderivative of the function g. This is taking derivative of that antiderivative, and that gives you the function. Okay, one undoes the other. Okay, there are times when this form is convenient in solving differential equations. For example, if g is continuous on an interval I containing x0 and x, rather than a at x, x0 and x, then a solution of the simple initial value problem dy dx is equal to g of x, where y of x0 is equal to y0, just some function, okay, some value, sorry. That is defined on the interval I, your solution. So here's the equation you have, the differential equation. dy dx is equal to g of x. Okay? the initial condition is y of x0 is equal to y0. Now, to me, that's more like a boundary condition, not an initial condition, but this book calls initial is fine. I don't care. Okay. And the g of x is continuous on the interval I. Okay? Now, what would we do before? Write it in differential form. dy is equal to g of x dx. Integrate both sides. Y is equal to the integral of g of x dx. Okay? Except they rewrite this, oh, and plus c. Okay? And we say that y at x0, so that would be is equal to y0. Then this would be y0 is equal to the integral of g of x0. That's not right, quite right. Okay. So, no, I'm sorry. You wouldn't include the plus c. Sorry about that. Yeah, because yeah, you by doing the yeah you don't need that because that's what your initial value or boundary value was taken care of. Okay, now that's what that is. So what that leads to then is, since that's true, and when x is equal to x0, that's your y0, then your function then is y as a function of x, for all values x, would be that y0 plus this. Now, rather than saying the integral of dx, g of x dx, they write that as x0 to x g of t dt, which basically, if you were to evaluate this, okay, that would be the integral of g of x dx, if you put that in for t, minus the integral of g of t, g of x0, the g of x0 is y0. So what we wrote here is a plus c. That just says that this plus c is your y0. I mean, it's just a different way of writing it, okay? And it says you should verify y of x in the manner. Since the antiderivative of the continuous function g cannot always be expressed in terms of elementary functions, for instance, the one we had on here before could, this might be best to do in obtaining the explicit solution for the initial value problem, IVP. When I was in grad school, I was a member of InterVarsity Christian Fellowship. They had a press called InterVarsity Press. So when I see IVP, I don't think initial value problem, I think InterVarsity Press. So forgive me if I get crossed up. Okay, so let's do example 5. I think it's going to be easier than what it seems, Well, yeah. Okay. Let's erase all ink on the slide. Okay. dy dx is equal to e to the minus x squared, where y of 3 is equal to 5. Okay. Now, how would you normally begin? Yep. Yes, definitely. You're not multiplying by dx, are you? Okay. E to the minus x squared dx. It just looks like that's what you're doing. You're not. You would never think of that. Okay, and this would be y is equal to, now, what is the integral of e to the minus x squared? I don't even think, I think they have a little integral table at the beginning, brief table of integrals, and
Exponential is just e to the x.
yeah, that's all they give you, e to the x sine dx.
So how are we going to manipulate this to get it
Yes.
integrated?
Okay, and that's what the whole, and they have e to the au cosine bu, but they don't have anything such as that. Okay, now, you might say, would a substitution help? It would if you had a minus 2x dx or any kind of x dx. You don't, so that's not going to help. Okay, so what we do is go back to their kind of finagling that they did. Okay, and we because they have the boundary value, we're going to do a little bit differently from what we did before. So let's erase just some of this. Okay. Okay. The first, since they've introduced this dt in there, they're going to do a dt on both sides. Now, I'm not sure that's all that necessary here, but in fact, it seems like it just muddies the pot a little bit. But let's humor them. Okay, so we're going to rewrite this as the integral of dy dt dt, which is dy, right? But now your t is going from 3 to x. Okay? Strange way to do this, okay? But obviously it works, so we're going to deal with that. And this will be, just like we've written it here, integral from 3 to x, e to the minus t squared dt. Okay. Now, what this gives you is y of t. We've introduced this parameter in here, but it's going to be evaluated from t is equal to 3 to t is equal to x. That's how we're going to get our y of x back. Okay. And over on this side, there's nothing we can do. We leave it just like this, 3 to x e to the minus t squared dt. It looks like we're just avoiding the problem. Okay? All right. Well, when we plug in, we get y of x minus y of 3 is equal to the integral from 3 to x e to the minus t squared dt. Okay? Well, y of 3 is 5. So that would then be y of x is equal to 5 plus, yeah, because it's a minus 5, so you add it to both sides, integral 3 to x e to the minus t squared dt. And guess what? We say we've solved the problem. Okay. All we did was leave it in an interval. Okay. Now,
you moved the 503.
yeah, we moved the 5. That's all, folks. That's all we did. But remember, that's an integral we can't solve. So what we're going to do is, what we're going to do at the very end of the term, if we get that far, the last chapter is numerical integration. So whatever value x you put in there, we're going to, numerically integrate that and come up with it. Okay? Now, we've just seen in that example, some simple functions do not possess an antiderivative that is an elementary function. Integrals of these kind are called non-elementary, and the one like we just did, that one, you basically limit. Sine of x squared is another one. There's tons of them. Okay? We'll run into this concept again in 2.3. Thank you for warning us. Okay, in some preceding examples, we saw that the constant in a one-parameter family of solutions for a first-order differential equation can be relabeled, strange word there, especially when they break it like that, when convenient. Also, I don't think this, I don't know. Their remarks can get pretty deep. Homework exercises. Do any of the odds, I think we checked and said.
Yeah, they're the odds.
Yeah. And is it all of them?
Oh, no, this is the one that
This is the one that doesn't have them all. But I think for most of these it does. So but I want to check every time. I don't want to give you things that you can't look for. Okay. Here's 2.2. You can do any of the odds 1 through 21. Are all those back there?
Yeah.
I think so. Then you can do any of the odds 23 through 27. They're all there. Do 29. That should be there, right? Yep. Do 31 or 33. Both of those are there. I thought they would be. Any of the, well, no. Do 37. I'm sorry. 35 or 37. Those should both be there, are they? Yep. Then do either 39 or 41. Those should both be there. Yep. Do 43. That's there. No, it's not. Forget 43. You can read through it, see if you can figure out what it's talking about, but don't sweat it if you can. Any of the odds 47 to 49, those should be there. Yep.
57.
Huh?
57 is the only one that's left.
Okay. And that's a mathematical model. So discussion problems, you can read through those if you wish. Don't sweat it. But 57 is a pretty lengthy problem. Lots of discussion there. And I'm trying to see where the question is.
Which one?
For 57. They have an answer, but what in the world is the question? Oh, wait, you're right. It's right at the end. Use this information to set up and solve appropriate initial value problem, which is the shape of a curve with okay. Okay. So if you want to tackle that one, knock yourself out. Okay. The rest of them you can look at. They're computer lab assignments. They require computer algebra systems. I don't have it. If you have it, feel free to follow it. Okay, how are we doing on time? Huh? Out of time. Okay, we'll begin next time with 2.3. So I will